This is where we left. Just to be sure, I will repeat the explanation. So if it is assumed that all 52 choose 5 poker hands are equally likely, what is the probability that you get exactly one pair? And then what's the probability of getting 2 pairs? So for part A, I imagined this type of document. And in this document, you list the pair number, and then you list the suits that correspond to the pair number, and you present them in order from smallest to largest. So you assign numbers to the front of the car. So let's say 1 might indicate ace, 2 indicates 2, 3 indicates 3, and onwards, right? 13 might indicate a king. And then you do the same thing for the suits. You assign numbers 1 through 4 to encode for the suits. In the presentation here, you write the smallest suit value and then the largest suit value. And then you select the remaining front numbers here, put them in order, and their corresponding suit numbers. So once you see it this way, it's clear that the answer is 13 choose 1 times 4 choose 2. So those two, the 13 choose 1, 4 choose 2 is the information in the first 3 boxes. And then you have 12 choose 3. That's information here. Times, so this is 4 possibilities, 4 possibilities, 4 possibilities, right? Because why 4? Because those are all distinct values, so they can have each particular distinct value can have any of the suits. Okay, and so the idea is very simple. It's that if I can come up with a code, and the code translates to an outcome, and an outcome translates to a code, all I have to do is count the codes. In B, my code system is slightly different. I just will have first 2 boxes will be the values on the pair. So this means this number I will see double on my cards, and this number I will see double on the card, in my collection of cards in my hand. Yes. So there are how many possibilities? 13 choose 2 to fill in this information, because once I have 2 pairs, I can present the smallest pair value here and the larger pair value afterwards. Good. And then what do I have here? Here I have the corresponding suits. So how many do we have? We have 2 suits will go to describe pair 1, and another 2 suits to describe pair 2. Good. So there are 4 choose 2 possibilities of filling this information, and 4 choose 2 possibilities for this information. So far, everything clear? And then I decided to have 1 box, and then I use the population number. So this number cannot be any of the values that were mentioned here, right? So it cannot be this number, it cannot be that number. Those numbers appear, so this number appears in 4 copies, and this number appears in 4 copies. So altogether, I have 8 copies that I cannot use. So it's 52 minus 8, choose 1 that you can put here. Alternatively, you can say that I have only 11 remaining values to choose from, and 4 suits for this value. So it's also 11 choose 1 times 4 choose 1. Okay, so this is my probability. I just I have the numerator, denominator is easy, and so the probability of having 2 pairs is well, it's less than 5%. It's not likely, right? But on the other hand, the probability of having a pair appears to be about 42%. So just 1 pair exactly, about 42% likely. 2 pairs, far less likely. And now let's consider poker. Let's consider poker dice. So it's played by simultaneously rolling 5 dice. What is the probability of 2 pairs? Now it's your turn. Let's see if you can come up with this answer. So you understand, you have 5 dice, you throw them. I'm asking for the probability of 2 pairs. So, Paulina, how do you obtain the numerator? Could you write it out? So you have a numerator, and I mean, I do not know the answer, what the numeric answer looks from the top of my head. But if you can write to me how you carried out the procedure for the numerator. So for exams, even though exams are not too scary for us guys, yeah. So I will do two things, right? One thing is I might not bother you if the answer is right away correct, but if I don't see an explanation, a Kafka document, I might just deduct all the points. I want to see how you're reasoning it. Y 15 times 4 times 3 times 30. So let's just a second. I'll think of it. You continue thinking, guys, and I'll think what's the thing here. So okay. You're not guessing. It's good. It's good. So let's see. So we have 5. So mostly it looks, Paula, mostly what you're doing looks good. Let me just see. So one thing, Paulina, are you thinking in terms of the document? Right, so it's very easy to multiply by something extra, or not multiply by something extra. I do advise that the way you know if you're right or wrong immediately is you have you visualize exactly how you put the information in and what you're counting. So I think you are right though. Yeah, I think Paulina, you're right. Let me know when you want me to proceed, guys. Yes, Naomi, very good. Ready? Okay. So again, I imagine that every single die is distinct. Maybe it's colored. Maybe one is white, next is red. You understand? There is something that I can observe about them, that each of them is distinct. I can always imagine that since they are objects that are simultaneously in different places at the same time, right? So then denominator will, the way the outcome in the sample space is described is what is the first die revealing, what's the second die revealing, third, fourth, and fifth. Good. So there are 6 to the power of 5 possibilities for the denominator, because this one has 6 possibilities, 6, 6, 6, 6. So it's 6 to the 5. Now, how do I partition? So in my presentation, and do something like this. You don't have to write it just as elaborately as me, but I want to see how you get your answers. Okay. So if you miscalculated something by accident or because it was misunderstanding, this really helps me understand what you're imagining. So I have this box for a pair of the values. So maybe the pair of the values, the smallest value that was repeated is 2. That's there is a pair, two dice are showing the value 2, and 2 other dice are showing the value 4. So I have 2, I put it as 2 and 4, okay? And then what is the single value? So maybe the single value that came out is 3, right? How many possibilities are there to fill this information just for the values? Well, there are 6 possible values. We have 6 choose 2, double values. So we choose 2 distinct values, and then we are left with 4 unused numbers, right? So we have 6 choose 2, we use 2 numbers. In this case, the numbers were 2 and 4. Now I have 4 extra values remaining. I choose one of them, and that was the 3 here. And then in this box, I decide which dice we're carrying what information. So you see, I put a dashed line here. So dice 1 and 3, we're carrying the value 2. Dice 4 and 5, we're carrying the value 4. And dice number 2 carried the value 3. Understand? So the code, in other words, when I look at this code written this way, 2, 4, 3, 1, 3, 4, 5, 2, I right away can reconstruct the actual situation. Here is what happened. Okay, I read this code, I can construct the picture. That's how I know I'm right. And every picture I can put into a code. Make sense? It's easy, right, guys? So the idea makes sense to you, correct? So if you are confused about the problem, that means that you are confused about the objects that you're counting and how to file a particular outcome. This is the idea, that something happens and you have a procedure. You record this outcome systematically in the code like this. And you must ensure that your code system is able to record every situation exactly in one particular way. Good? And that probability is about 23%. Good? Now very quickly solve this problem. 9 dice are simultaneously rolled. What's the probability of getting 3 pairs and 1 triple? In other words, you have 3 pairs here, this, and a triple. And when you submit the answer, better not numerically, just tell me what algorithm you use to count. And maybe I'll ask you afterwards whether or not doing it differently is correct. Okay, thank you. So even in text, you're putting the information pretty well. Paulina, you got the same as Naomi or as interpret? Interpret. Okay. So I do hope, guys, to hear more from more than 3 of you. Good. So once you're done, let me know. I want to see that you will follow. Naomi, yes. You're getting it. You can remember, Bowen, we established that if you have random selection, sequential or simultaneous does not matter here. Okay, Kazi, wonderful. Wonderful, Chabeli. Shotaro, great, right? So you understand the codes. I mean, you might be annoyed by writing the boxes. Yes, Kazi, I will. But didn't you use that? You used it, Kazi. You used that. Of course, I'll explain that. But you used it yourself. So what about the others? That's very important, guys, right? Every single step, I'm hoping you're not just studying to survive this class, because it's not usually hard with me. Many people survive and get A's and then afterwards ask me for recommendations, but really it wasn't hard to survive this class. I hope you're studying for something else. So let me, before I continue with the explanation, ask you whether or not this solution is correct. And if not, you will try to critique the solution. Okay, ready? Let's try if this instrument works this time. So suppose that, I wrote something like, let's say first I have 6, choose 2, correct? 6, choose 2 for the first pair, and then I used up, oh sorry, not 6, choose 6, choose 1, my apologies, right? 6, choose 1. So I wrote 6, choose 1, that's the value for the first pair. Then I have 5 remaining numbers. I choose one of them for the second pair. And then I have 4, and I choose 1 for the third pair. And then I'm left with how many? I'm left with 3 values. I need to choose one of the values. So I have 3, choose 1 for the triple. Okay. And then finally, I need to describe which dice are picking which value. So I would say it's 9, choose 2, 2, 2, and 3. Yeah, is this correct? What I wrote here, or something is wrong here? By the way,
the exponent is 9, right, on the bottom?
Oh yeah, it should be 9, but that's not what I meant, right? That's a trifle mistake. Yeah, so the exponent is 9.
Yeah, it looks correct.
So looks correct. Bowen looks correct. How many of you say this is correct? None of you answered this question this particular way, notice, right? Everybody that answered it did something else. Is this solution correct? And by the way you can also indicate Kafka protocol. You can say, for example, this is first pair, right? This is second, this is third, this is triple. You understand? You can indicate your Kafka protocol somewhat like this. Paula, can you hear me now? So your computer froze, but now it functions, correct? Yes, wonderful. So everybody here in my small dwindling classroom agrees the solution is correct? Naomi, Shotaro, Chabeli. Yes. Oh my God! Yes, it's a cascade. It's like the earth is sliding once it rains. Maybe Chabeli says, right? Let's see who says correct, so that I will note you for the future. Naomi said she thinks so. Sayed says I think so. Think so is very diplomatic. You're studying to work at the UN. Bowen, yes, you're brave. I will send you over the trenches as soon as the next war is beginning. You will lead the troops. And also get a bullet in your head because it's incorrect. Okay, it is incorrect. And the reason it's incorrect is because you did not file a Kafka protocol correctly. You didn't check it. It's incorrect. Now, why is it incorrect? Because what makes a first pair, second pair, third pair? This means that somehow that was the first pair that was picked. You know, you throw the die. We're not even sure what is it that you're throwing, right? Are you throwing one dice or many, right? If you can simulate throwing 9 dice if you don't have them by throwing one at a time. You understand? But if you throw one at a time, you are actually solving a different problem. You understand? We in the denominator. What we're assuming is, well, let's be careful here, right? So if you throw one at a time, it's dice 1, dice 2, dice 3, etc. Right? You can here is the problem, right? So what do you mean by first pair? First time I get a pair, right? What is first pair? It's not clear what first here refers to. The document is unclear. How if I were to write a code, what do I record as my first pair? You understand? So if you can throw one die or many, and then you see a bunch of numbers, what do you mean by first pair? It has to be extremely clear. If I have to execute your protocol, what do I write there? And you understand what happened here in this algorithm? You are overcounting because you see when you say first pair. Okay, so let me see if I can show you some more of it. Let's try to open up one second, a whiteboard. Okay, so we have this whiteboard here, and let's see what could have happened here. First of all, it's entirely not clear what first pair means here. So let's say maybe what you got is are those outcomes. So it's 2, 4, 4, 6, 6, right? So imagine it just actually happened like this. 2, 2, 4, 4, 6, 6, and then we have a triple. The triple was 1, 1, 1. Okay. So this is you say first, second, and third. But any rearrangement, so for example, if you had 4, 4, 6, 6, 2, 2, right? It's really the same pattern. Let's say 1, 1, 1. It's the same outcome that that occurred here. Not quite. Let me correct myself. You see, suppose that you have first of all this situation. You have, let's say, 2, 4, 2, 4, 6, 6, 1, 1, 1. So when you say first pair, one danger is, first of all, what do you mean? What is here? What do you call a first pair, right? Is this outcome different from, ask yourself, is it different from the outcome 4 to 4, 6, 6, 1, 1, 1? Okay. So I have to be myself careful. I hope I am not. Maybe I said incorrect, but in fact you were correct. I have to be careful, right? But here is my. I will think about it for something. It might be glitching today, to be sure, right? So you have to be very very specific about how your code is working. I think, right? What is your first value? What's your basically what do you mean by first pair? What do you mean by second pair? What do you mean by third pair? Right? I will return to this question. I might have said you are not right, but maybe you are. I just have to think about it, right? So, but basically, when you write, when is it confusing for me, for example, right? If I am not sure how the algorithm was carried out, what is it that you exactly did when you were counting it, right? So for example, the ambiguity lies especially when you say 9 choose which when you add this information about which die picked which value. You see, how does it come together with first, second, third pair, etc. So let's get back. So you see, with this document, I'm being rather precise about how the information is presented, right? So I present the values that I received. Yes, the values that I received. And then I present the particular die that carry those numbers. Okay, so I list them in order from smallest to largest. So this information can right away clearly be translated to the pattern. So this is definitely true. I will return, if you want to talk about it in office hours, I will return to the way I asked this problem, and we will examine just to be sure if I haven't glitched, if this was right or wrong. But you see, as soon as there is ambiguity in the pattern, then you do not know if you are right or wrong. Okay, so I just want to be sure again, right? I think maybe I jumped in my head prematurely, said it's definitely incorrect, but let me afterwards verify what is the pattern. If you definitely, if you have this protocol and you know exactly what you're counting, you will not get confused. I see. Good. So next question is this. So we have a game of bridge, and 52 cards are dealt equally to 4 players. So what is the probability in A that one of the players receives all the 13 spades? Yes, it seems the old Arkady was not glitching, right? Just try to verify by calculation first, but then we will talk about it. The other solution that I offered was incorrect, but if you want to, we will talk about it after class. I hope you will stay. Remember Kafka Protocol, right? If you don't do it, you will confuse yourself. It has to be very clear how you are counting. once you already type the solution in the comment. Okay, Alejandro, let's see what you're saying. So Alejandro, your answer does not account for what other people are receiving. So there are 4 players here. Let me think before I continue on, because you might have selected a clever space. I think you're right. My apologies. Can, yes, very good. Now, me, you say the same as Alejandro. It's this is actually very, very dangerous. You have to you think of it two ways. What's the sample space? Okay, you have to visualize the sample space and what is it that you're counting. Otherwise, it might be correct or it might not. You have to really be sure that you have it. So definitely the probability that a particular player gets 13 spades, if you fix your attention on one player, is 1 divided by 52 choose 13. That's true, because he can get any grouping of cards, but does it translate to one of them it's times 4? That you have to be careful. Because if so, what is the full sample space? If you talk about other players, then how is it included in this information? Every time, guys, you do not see what you're counting, you don't have a Kafka protocol, for me for sure, right? I will have difficulty deciding whether it's correct or not. And you too, you might have difficulty deciding whether it's correct or not. So Shotaro, you say also the same as the others, right? So you're going with 4, choose 1, 52, choose 13. All right, let's look at the solution. So the solution that I get here is 4 times, yes, so it's 4 multiplied by the reverse of 52, choose 13. So the solution is correct. Good. We can think of it this way, right? So we can think of this as, let's suppose, what's the probability that player 1 gets the 13 spades. So player 1 can get any collection of 13 spades, which means that probability is 1 divided by 52, choose 13. Yes? And the probability to want is either player 1 or player 2 or player 3, etc. And those are disjoint events. Yes, that's always a good question. You understand, guys? So it's a clever type of, and many of you might have kind of a sense or a feeling of what it is. But whenever you do not have a Kafka protocol, you can be mistaken. You understand? So Kafka protocol, if you visualize the sample space, what you're counting, and you produce the protocol, you can be sure that you're correct. If you're doing something else, the certainty begins to vanish. Okay, so what's the Kafka protocol for this document? Let me try to draw one for you. How I would possibly do it. So, one second, new share. Let's do the whiteboard. Yeah. So what would you do here? I would say, first of all, the Kafka protocol will tell me which player. So for denominator, it's clearly, so denominator, if I account for all the players, let's consider the situation as it happens, you understand? Let's not reduce the sample space for this problem for one moment, okay? when you reduce the sample space, you are also running the risk. You need to be sure what is it that the sample space that you reduce to, right? So the denominator is clearly going to be, it's going to be 52, choose 13, 13, 13, and 13. Yes? That's my denominator. Everybody agrees. If I account for all the players, if I consider my sample space to talk about what all the players are getting, okay? And then what would be my Kafka protocol for the numerator? So numerator means that I observe the outcome or observed an event when one of the players received 13 spades. So one box will tell me which player. So maybe player 1, you understand? So this has exactly 4 possibilities. You agree? Because it's either player 1 or player 2 or player 3. And then I need to account for the remaining cards. So player 1 received all the spades. Now, what would be the situation for the other players? Well, I would have this type of box, right? So here is a box, here is a box, and here is a box. So this requires 13 cards, and 13 cards to be ordered equally. We have remaining 39 cards. Do you agree? 39 cards because I took 13 out. So so that makes it simply 4 times 39 distributed to 13, 13, and 13. So if this is player 1, this is for player 2, player 3, player 4. You understand? If I put here instead of 1, I put 2, it will be all the players except for 2. So this I can be sure it's not necessarily right now the best type of calculation-wise, the best type of argument. And by the way, somebody asked me about this type of structure. In this game, who are the dragons? For the numerator, who are the dragons here? Okay, so the dragons here are the players, right? The players who eat the cards. So we have 39 cards distributed. Their destiny is to go to this player or that player or that player. Okay, so whenever you have distinct knights distributable among dragons, then that's this multinomial coefficient. Good. So if I think of this form, I can be certain that I'm not making a mistake. Okay. And when you do like what Alejandro, Shotaro, Naomi, and other people did there, unless you visualize what is your sample space, you're running danger. You see, because you visualized, when you did that, you visualized an entirely different sample space. You just focused on the one player who gets 13 spades, and you ask, okay, what's the probability then? So here is the sample space that that many of you did. It's a better sample space, but there is a danger. You understand? Imagine that I know that player number 1 received all the event where player number 1. So I consider, so to speak, probability of R1. Yes, that means that player 1 received all the spades. Yes, and then what were the possibilities? So player 1 received all the spades. The possibilities were for this player to receive any other 13 cards. It's clearly true. It seems that there is no preference to what the player receives, so it should be true that this player could receive any number of cards, right? And that, in other words, any types of cards. So that means that we can use the same counting thing for the numerator and denominator, except for the numerator, the spades, let's say we label them as 1, 2, all the way to 13, listed in order. So there is only one possibility for the numerator. And for the denominator, we can select any number of 13 cards. So there are exactly 52 choose 13 possibilities. So here I decided to label the spades as 1 to spade 1, spade 2, spade 3, etc. Right? So there is only one possibility for this outcome. So it's really 1 divided by 52 choose 13. That's clear when you have one player. But when you are multiplying this, so here you might be using something else, you understand? So here you have not constructed the Kafka protocol corresponding to all the players simultaneously, but you're doing yet another strategy, okay? Let me show you what's the strategy, why it worked, right? So I actually switch in the middle of the problem from one sample space to another. Okay, because we can do it this way, right? So probability that spades were received, probability that all the 13 spades were received by one player is enclosed in the probability of R1 union R2 union R3 union R4. You agree? So here I am considering my original sample space. You understand when I say R1, R2, R3, R4, I consider my original sample space. You with me, guys? Right? And with the original sample space is what I did when I solved this problem the hard way. Now, because those events are disjoint, yes, so understand, guys, I want you to be always very careful about your reasoning, right? Because if not, it can lead to error. So why did your solution work? Well, you're using original sample spaces, and so that, in other words, you begin the problem by considering the situation for all the four players. So you see, when I say R1, R2, R3, R4, I actually, my sample space accounts for all the cards, or for the particular cards that were received by each player. But then I can write it as basically summation, where k is 1 all the way to 4 of p r k, which, because by reasoning that there is no preference which player will receive it, so it's equally likely that it will be, if one of the players received the cards, it's equally likely to have been player 1, player 2, player 3, and onwards, right? So there is symmetry in those distributions. So again, intuitively, you right away recognize that it's really 4 times the probability of R1. Yes? But now, and that was very clever, now what you do is you realize that probability of R1, if I consider all of them simultaneously, or just one of them, ends up being the same result. So here, once I calculate probability of R1, I suddenly switch to a different sample space. You understand what happened here? You were not working with the same sample space, at least the way I'm seeing the problem right now. I was not working with the same, or Alejandro was not working, or Shotaro. You were not working with the same sample space. You understand? So now you switch focus. Now you forget about the information. So you say, oh, so what's the probability that player 1 receives 13 spades? That means we can now say, well, player 1 could have received any number of 13 cards. Yes, any number of 13 cards. There is no particular preference. So then the probability is 1 over 52 choose 13. Good. And still, this type of reasoning always makes me worried. You understand? Because you understand, you jumped from talking about the entire population to talking about just what this particular person gets. So you're using a sort of symmetry here. Okay. Good. Okay. So yeah, so then how do you solve the next problem? So the next part is part B. Each player receives exactly 1 ace. So my advice, guys, whenever you have any doubts, you always construct, you always check with the sure method, okay? If you have a doubt, solve it using the Kafka protocol, because that is infallible. Not always simplest, but always true. Very good interpret. Okay. Alejandro, very good. Because, Bowen, why do you multiply by 4 factorial? I'll explain in a moment. Why do you square? 4 choose 1 square, Shutaro? I think you mean not squared, something else possibly. So let's view the solution, and we'll explain the 4 factorial. And guys, how do you eliminate questions? You say so. It's good. You can be trying and daring, but always, right? Always the best way to avoid mistakes is Kafka protocol. Okay, so check whenever you did something where you were not absolutely using the sample space. Always verify with Kafka protocol. If you don't have it, see, so you might have an intuition, or you might kind of jump through things, but without surely knowing what you're counting, you will make mistakes, or could make mistakes. So here is, so I always have it in my mind. Okay, here is the solution, and many of you put a 4 factorial here. Why do you put 4 factorial? Well, let me show you with the Kafka protocol. Why 4 factorial? Okay, so what's the protocol for the numerator, right? So we have each player gets one ace, correct? Each player gets one ace. So aces, let's label aces as ace 1, ace 2, ace 3, and ace 4. Good. So I have this box here. Sorry, it's not too pretty, but you understand. There are 4 boxes. This is A1, A2, A3, and A4. And so here I put numbers 1 through 4, right? So here I have, okay, 1 second. Naomi, you're back? Because Naomi also had the same question. You there, Naomi? No, no worries. It happens. Great that you're here. So basically, I said A1, A2, A3, A4. Those are my aces. I labeled them 1 through 4, and players are also labeled 1 through 4. So I need to know which player got which ace. So which player got ace 1? There are 4 possibilities here. There are 3 possibilities here. 2 possibilities here, only 1 possibility here. You agreed? So that's where the 4 factorial comes from. So here you have a 4 factorial. Next, I know the aces. Next, I need to know how the other cards are distributed. The other cards are distributed. I can make it just a big bar divided into 4 segments. Right, 4 segments, and those are cards for player 1, player 2, player 3, player 4. Yes. And now, I mean, you can write them, you can invent a sort of notation, doesn't matter, because it's not quite multiplication that I mean here. So I create this type of notation, I just do something like, this, right? So between the players, I make this separation because they're all together, right? So all together, what I do is I have now 52 minus 4 cards, and out of those, so those are the remaining cards that needs their destinies. 12 of them will go to player 1. He's the dragon. Player 2 will also get 12 and 12 and 12. Yes, that's the numerator. Make sense? So, and I can be absolutely certain that I'm correct by solving in this way. If you solve it with any other technique, if you even jump through sample spaces, we'll talk about it later. There is always the sense that maybe something is tricking you. Maybe you assume there is similarity or something where is none, right? So you're always running that risk. Great. So let's go. Let's see what else we have here. So we did not quite get to that point. Do you want to do a comprehension check, or you want to go home? Okay, so one person wants comprehension. By the way, guys, stay in office hours. We can discuss what we haven't. So for example, I thought about it. I think I can explain a bit better why that thing was incorrect than what I did, okay? It was just a spontaneous kind of thing. Spontaneity can be dangerous as well. So comprehension check, try to compute 6 cards are sampled randomly from a regular deck of 52 cards. Calculate the probability of being dealt 3 pairs. You have 6 cards that you sample. Of course, if you have to go, guys, you go. It's lesson is over. You have it on video. I'll stop recording only once office hours begin. So interpret any announcements. No, there were no particular announcements. Only I asked about the birthday thing. We haven't reached it just today. Only 13 or 12 people replied, so the probability of success was it was 13% actually. So and success did not happen. I need more people. Then I can show you what it is. And guys, one thing is, of course, you know you have two exams that are posted on my website. There will be another one. You want to do all the exams, and because it's interesting, we don't want to lose any questions and all the homework, right? We want to be really great at the subject. Yes, Melissa. That's brilliant, Naomi. There would be one more question if I want to know if another solution is correct. When you're ready, guys, let me know. Yes, well, Naomi's solution is right. No, Melissa, don't go. I should play your beautiful song. You know, "Не уходи, побудь со мною." You have to go right now, right a second, or should I play the song? It's okay. You have to go, right? You have to go, you have to go.
Well, first, how long is the song?
Well, let's see. Let's see how long. Give me 2 seconds then. It's 3 minutes 38 seconds. Too long?
Send me the song and I will
Okay,
listen
well,
to it.
it's not as interesting. Okay, take care then.
It's not that, but I do have to go. So thank
No, I
you.
know, it's okay. I'm joking with you. A good one. I'll play it for the others, I guess. Maybe they will not leave me. You can hear it, right?
Побудь со мною, здесь так отрадно, так светло. Я поцелуями покрою устаю.
Yes, exactly. How do you know, Bowen?
Я поцелуями покрою устающий. Побудь со мной, побудь со мной, не уходи, побудь со мною, я так давно тебя люблю, тебя я лаской огневою обожгу и утомлю тебя я лаская гневою. Обожгу и утомлю. Побудь со мной, побудь со мной, не уходи. Побудь со мною, горит огонь в моей груди. Восторг любви нас ждет с тобою. Не уходи, не уходи. Восторг любви нас ждет с тобой. Не уходи, не уходи. Побудь со мной, побудь со мной.
I couldn't resist it, you know. Yeah. You understand what it is, guys. If you haven't heard it before, it's not just a nice song, it is an amazing song, right? It's a Russian song. If I could sing, I would. It means, do not leave, stay with me. I will burn you with my kisses, right? With fiery passion, I will tire you, which is exactly what I'm doing to you. So let's you know, learn Russian. And Bowen, my God, you speak Russian? Do you understand Russian or what? Well, we'll need to make it a lot, right? In fact, I want to transition into teaching this class entirely in Russian by the end of the semester. Okay, so comprehension check. 6 cards are sampled randomly, and we have 52. So again, no, me and some other people solved it absolutely correctly. Let me show you using on the whiteboard why. Okay, so what's our solution supposed to do? So first of all, we are supposed to pick 3 pairs. So I will create this. So then I have, this is for small value on the pair. This is for medium value on the pair. This is for large value on the pair. I can arrange them. So that means that I have 13, choose 3 to place information into this box, correct? Because I choose 13 values and choose 3. So next, that's all the cards I have, all the front numbers. So then each card has 2 suits that correspond to it. Yes, 2 suits. Each suit. So this is the middle suit. There are 4, choose 2 possibilities here. So numerator is simply 13, choose 3, times 4, choose 2 cubed. Right, so I just cube this thing for the numerator. Now, let me ask you this question, guys. Would that be a correct solution for the numerator? So I have, let's say, I begin with 6, choose 1, right? And then I have 5, choose 1. So that is first pair, second pair, 4, choose 1, third pair. So this would be, and then I have the suits. The suits would be 4, choose 2 cubed, right? So would that be correct or not? So this I'm saying first pair. This is second, and this is third. Is this correct? And then let's see. And then in the denominator, of course, it's it's 52, choose 6 in this case. Definitely no. So what's wrong with this, guys? What's wrong? Why is it not correct in this situation?
Is the sample space on the numerator and the denominator different?
Well, first of all, there is no clear sample space because you mix up. What is the 4 choose 2 cubed, right? Why is it 4 choose 2 cubed, first of all? And when you say first, second, third pair, just that, you are assuming that, well, what is the first pair to begin with, right? Do you mean that I actually do it consecutively? I picked somehow, which is again not very clear. How did I pick those cards? You see, there is this, first of all, ambiguity problem. What do you mean by first? Yes. Yes. What do you mean by first? What do you mean by second? What do you mean by third? When it's ambiguous, it's not clear exactly what are you counting. That will generate many mistakes. Good. And that was the same situation in the previous question. I can show you, I think, maybe a little bit better what can go wrong, right? Just when you read it, it has to be so. When you read it, it has to be clear what is first, what's second, what's third. What is it that you multiply? Yeah. Otherwise, you will generate many mistakes. Any questions on that?
So for like when you say the first pair, it could it doesn't have to be the because a pair, I'm assuming, has to be the same two numbers. This doesn't specify that it has to be the same two numbers.
Well, it's not clear. So pair, let's say pair means I recognize two numbers, but the question is how am I going to place this information? What's first pair? What's second pair? What's third pair? Right? So that's one. That's the immediate. So you're telling me just put first pair, put second pair, put third pair. So let's consider just pair values, right? Pair values. So what can happen here? So let's see. If the outcome is 1 1, maybe 6 6. What I mean only front numbers, right? 6 6 and maybe 12 12. It's clear that maybe this is first, this is second, this is third. Yes. If those are the particular numbers that appeared. But what if the numbers appeared like this? Is this what I consider? Is this a different outcome? You see, you have to be sure, is it a different outcome or is it the same outcome that happened here? Right, because let's say what I multiply is afterwards by 4 choose 2 cubed. So that I am assigning so 4 choose 2 for first pair, for the second pair, for the third pair. Is it a different outcome? And you can realize that if I say this is first pair, this is second, this is third, they do not appear in order. The cards, by the way, I'm counting with the I'm having them simultaneously. So that's the same outcome, which according to your methodology, it now says it's not, because first, all right. So it's basically the same cards appeared. You understand? So imagine this, and then we have, let's say 1 2. Suits is 1 2 1 2 1 2 1 2 1 2 1 2. So 1 2 maybe hard spades to ignore it, right? This is the same outcome because my collection is unordered pairs based on the structure, right? It's just unordered pairs. I just rearrange it. And if it's not unordered pairs, if you do it sequentially, then how are you doing it sequentially? Because what happens if you have something like this? If you have 1, then 12, then 1, then 6 6, and then 12, right? What do you do then? Exactly how do you talk about such situations in this discussion? What's first pair here? Okay. So if it's by the order in which card appeared, it's very unclear. Well, how do you decide what's the first pair here? And if it is, if first is basically you just as soon as you can say, well, the first pair is you scan the full list, and as soon as you identify first number that belongs to a pair, you consider it a first pair, then you generate overcounting. Understand? So let's say if I say, well, first pair will be the first number that I notice that repeats. So here 1 is the first pair, right? And then second pair according to that will be 12, and third pair will be 6, I guess, right? If I have this type of scheme, then those two outcomes, numerator and denominator, are going to be counted as different outcomes. Yet they are because we are in the denominator, we calculated it as an ordered grouping. Then it will create overcounting. Make sense? Good. Do you have other questions? Anything you want to discuss from before, from now? Solve some problems that you were stuck on or were confused or want to hear other explanations for? And it's good time to do that. Okay, Naomi, I figured that's what you're going to say. Okay, Bowen. So we'll need to check what's your Russian level. Okay, so you're leaving me. Then take care.
Hey, Professor.
Yeah, how are you, Shotaro?
I'm good. Right now what I'm struggling with is trying to, I guess, stay in the same sample. It's hard for me to come up with, like, especially for the numerator, the Kafka document, to like properly get them out like you need. Like all the.
Let me actually stop this recording and then yes, I forgot to stop it.